Hello everyone, we're going to go through another example today. We're again finding the complexity of a recurrence relation, but this one is slightly different than the ones we've experienced in the past. We notice there's a coefficient in front of t, and we'll see how that impacts all of our analysis. So let's begin by doing everything the same as we have in the past. We're going to take whatever appears inside of t on the right-hand side of the equation and plug it back into the equation. As we've done, we maybe want some sort of master designation for it, so I'm going to denote it with a little purple line. And we're going to want to plug n minus 2, the thing appearing inside of t on the right-hand side, into our purple lined equation. Doing so, we get, let's do it in black still, t of n minus 2 on the left-hand side is equal to 2 times t of n minus 2 minus 2, which is n minus 4, plus c. We don't need to do anything with the c because there is no n appearing over there. So now we're going to take the right-hand side of this expression, underlined now in blue, and substitute it in for t of n minus 2. Doing so, we have that t of n is equal to 2 times 2t of n minus 2 plus c. That's from our substitution. Then we have that additional plus c hanging out at the end. Maybe we do a bit of simplification here because this looks really messy and I can see that ooh, this should be an n minus 4. I'm quickly going to go down some horrible rabbit hole here of having too many parentheses, so I'm going to distribute that too, actually. So we get t of n equals distributing the 2, we get 2 times 2 is 4, t of n minus 4, plus 2 times c is 2c, plus c. And we're going to do a bit of black magic here. We have 2c plus c. Let's combine that into 3c. Now, we need to take whatever is inside of the right-hand side now, which is now n minus 4, and plug it back into the purple equation. So plug n minus 4 into the purple equation. So we get t of n minus 4 plus, not plus, is equal to 2 times t of n minus 4 minus 2, which is n minus 6, plus c. We now want to substitute the red underlined bit for t of n minus 4. Making the substitution, we have t of n is equal to 4 times 2 t of n minus 6 plus c, plus that additional 3c still from the original equation there. Now we need to distribute the 4 as we did in the past, so t of n is equal to 8 times t of n minus 6 plus 4c plus 3c. Looking at this, maybe we group together stuff again before we proceed, so we call that 7c at the end. We have here in red 8tn minus 6 plus 7c. There we have 4tn minus 4 plus 3c, and we had 2tn minus 2 plus c. The pattern here might not be so obvious, but let's try. So first, let's do this with green. If we look, the things out front, 8, 4, 2, those look like powers of 2. So maybe we notice it's like 2 to the k. And then t of n minus 6, n minus 4, n minus 2. The thing inside of t is updated by subtracting 2's. So maybe we say, that's probably going to look like n minus 2 times k, not to the k. This last term over here, the 7c, the 3c, and the c, we'll notice that's actually always 1 less than the coefficient in front of t, and that will always hold. So maybe we are very clever and notice that that is 2 to the k minus 1 times c. And again, it's 2 to the k minus 1 because it's 1 less than the thing in front of t. So this is going to be true for any value of k. So for any value of k, we have that t of n is equal to, my first term there looks like 2 to the k times t of n minus 2 times k plus 2 to the k minus 1 times c. So we have this expression. It looks ugly, but maybe it'll turn out nice. We now want to incorporate our base case. Our base case, scrolling up, was t of 0 equals c. So this will stop once we achieve our base case. So this stops when whatever appears inside of t, in this case it's n minus 2k, is equal to the base case, which is 0. We need to solve that for k, add by 2k, divide by 2, so we get k equals n over 2. We're now going to substitute that back into t, so we get t of n is equal to 2 to the n over 2 times t of, I don't need to do any math here, it's always going to be t of 0 because I chose k to make that happen, plus 2 to the n over 2 minus 1 times c. Notice we do not have a summation to analyze here, so we're actually really close to being done. We just need to identify the complexity. But you do need to be careful. We need to make sure exponents and constants matter. So 2 to the n over 2 is in theta of 2 to the n over 2. That over 2 cannot be ignored. So t of n is in, that doesn't look good, let's try that again, is in theta of not 2 to the n, but radical 2 to the n. Why? Well, that's because 2 to the n over 2 is equal to radical 2 to the n. The 1/2 in the exponent appears as a radical. So the complexity here is radical 2 to the n. We'll notice that this is a really bad complexity. This is exponential from almost any purposes. Just having an exponential runtime means you abandon all hope for the algorithm. So if you ever got a recurrence relation that looks like this, you might need to do other work.